Hello everyone. Today I will be presenting my work on data sanitization of aged SRAM array using ionizing radiation. So before I begin, I would like to acknowledge and thank our sponsors for supporting this work. This research was conducted at Colorado State University under the supervision of Dr. Vishwajit Ray. With that, let's begin. So here is the outline of today's presentation. I'll begin with the motivation for this work and a brief background on SRAM power-up state and torsional ionization dose. Next, I'll present our experimental setup and results. Finally, I'll conclude with the key findings. So, as we all know, discarded electronic devices from retired systems or e-waste pose a serious risk of data leakage. If sensitive information is not permanently erased, an attacker can potentially recover the valuable data. So, for non-volatile memories, this is a well-known threat because data remains stable even after the power is off. So therefore, data sanitization is necessary in such case. On the other hand, SRAM is a volatile memory. So the stored data is expected to disappear after power off. That is the assumption of every human. But interestingly, recent studies have shown that aging can leave permanent data imprints in SRAM array, allowing previously stored information to be partially recovered even after the power is removed. So this raises an important question. How can we securely sanitize an aged SRAM chip? To answer that, let's first look some of the existing sanitization techniques. So today, secure sanitization mainly relies on physical destruction techniques such as crushing or pulverization, chemical dissolution, shredding, or burning. While these methods are effective, they cause several limitations, such as they are not environmentally friendly, the chips are not reusable, so they get destroyed and not functional, and these are not applicable in space because they need a very high equipment and there are a lot of factors involved in this. So instead of destroying the SRAM, we ask a simple question. Can radiation erase the sensitive data when while keeping the SRAM still functional? So to answer this question, we propose a radiation-based sanitization technique using a cesium-137 gamma source. Now, let me give a brief background on a 6-transistor SRAM cell. As shown here, the cell consists of two storage nodes Q and Q bar, formed by two cross-coupled inverters using P1, N1, P2 and N2. When we power up the SRAM, VDD rises from 0 to 3.3 volts. So initially both PMOS are on, so both storage nodes begins charging at the same time. So this behavior is shown in the simulation plot generated using Cadence Virtuoso with a 180 nanometer PDK. So the key question is, which side wins? It is simple and similar to a two card that is racing. So whichever is stronger, that's going to win the race, right? So here we assume that P1 is slightly stronger, so the Q node is pulled towards VDD, while the opposite node Q bar is discharged through into towards ground. So this decides the power up state of an SRAM cell. So what would an SRAM power up state of an array would look like? So it is a pepper and salt image and it is repeatable for each chip and it is also unique for specific chip so that it can be used as a fingerprint identification for device identification. Since yeah, now let's look some of the how the aging affects the SRAM power up state. Let's see, like we write the cell with Q is equal to 1 here. So the P1 transistor is on, P2 is off, N1 is off, and N2 is on. So during aging, the on PMOS transistor experiences the NBTI stress. This creates differential aging between P1 and P2 transistor, where the on transistor threshold voltage is increased, which means the transistor which was on that gets weaker. So after aging, how the cell's power up state would look like. So here, after aging, it is clearly seen that the cell which was written as Q is equal to 1 is being flipped to Q is equal to 0 because the P1 which was on earlier due to NBTI stress, it got weaker. And this, we call it as a reverse imprint on a power up state. Now, this is for a single cell. How would an array of SRAM would look like? So to show that, let's assume that we are writing an Einstein image during aging. And what the power up state of an aged SRAM would look like in this case. So it's the complementary pattern of the Einstein image. This we call it as reverse imprinting on an SRAM array. Now, let's see how the radiation affects on the SRAM power up state. We again write the cell with Q is equal to 1. So during irradiation, the on NMOS experiences charge trapping, so its threshold voltage decreases, so the transistor becomes stronger. Let's see how the power up state would look like after radiation. So now, the cell which was Q is equal to 1 and irradiated will strongly powers up as Q is equal to 1. We call this as a forward imprinting. So at the array level, as TID increases, the Einstein image which was written becomes more clearly imprinted in the SRAM power-up state. This work was presented by our group at NSREC 2024. Now, with the background that is well established here, let's move on with the experimental setup and results of radiation-based sanitization. Here, we are using commercial off-the-shelf SRAM chips that is mounted into the T-sub socket and a custom designed PCB is used for interfacing. So the temperature chamber was used for accelerated aging and a cesium-137 irradiator was used for the process of sanitization. We have tested three chips across two different manufacturers, Cypress, which is commonly known as Infineon now, and ISSI. So there are three technology nodes that were tested, 90, 150 and 180 nanometer. All these three chips were of 4 megabits and operated at 3.3 volts. Now, let me walk you through the experimental flow. We begin with SRAM aging. Then, first, we measure the power-up state of a fresh SRAM chip. Then, we write the Einstein image and thermally age the SRAM. So, after aging, we read the power up state. So it is clearly indicated that almost 80% of the Einstein image is recovered after in the future power up state of an aged SRAM chip. Next comes the sanitization. We overwrite the aged region with a sanitization pattern. So here I have used a all black pattern which is contains of all zeros and expose the SRAM to gamma radiation and then read the sanitization power up state. What the sanitized power up state would look like. Since radiation causes forward imprinting, it imprints into the whatever the written pattern is. So here, to quantify the sanitization efficiency, we use Hamming weight, which is defined as percentage of ones in the power up state. So, and HW percentage, which is 100%, means that perfect sanitization for the cell that is written with all one pattern, while the HW of 0% indicates perfect sanitization for the all zero pattern. Now, let me demonstrate the radiation-based sanitization of aged SRAM. So, as we have seen earlier, we begin with the aged SRAM, where the reverse imprinted instant image is clearly visible. Next, we override the same memory locations with all zero data pattern and expose the SRAM to gamma radiation. Here, we use a cesium-137. As the total ionization dose increases here, the Einstein image gradually fades and washed away. So only a faint traces of remain still, demonstrating effective data sanitization on the chip. So let's now take a look at how the different technology nodes behave during the sanitization process. So the plot here shows the Hamming weight as a function of TID. The red line represents the white pattern sanitization, the black line represents the black pattern sanitization. So for the ISSA 180 nanometer node, the aged Einstein image gradually washed away. So at 50 kilorad, near complete sanitization was achieved. Similarly, the 150 nanometer here reaches the near complete sanitization but requires a higher TID. Now let's take a look at the 90 nanometer. Even at 100 kilorad, complete sanitization is not achieved. However, the recovery of the aged image here is drastically reduced. So this clearly shows that sanitization is more effective on the older technology nodes. Newer technology nodes will need a much higher TID to reach the near complete sanitization stage. Now let's see what happens when the irradiated chips are kept at room temperature with all pins grounded. So the plot here shows the Hamming weight as a function of relaxation time. So first, the ISSI 180 nanometer device, the sanitized pattern gradually relaxes and moves towards a new random data pattern. And similarly, the 150 nanometer also evolves towards a new data pattern after a couple of days. Now, for 90 nanometer, which was not completely sanitized, since a slight signature of the Einstein image appears approximately after 1 day. However, it is important to note that the recovery is only minimal. So to conclude this presentation, the TID effects can cause near data removal of imprint on SRAM power-up state, and the older technology nodes that are more effective to the TID-induced sanitization than newer nodes, which means older technology nodes are easier to sanitize, but newer technology nodes require higher TID. Also, compared to the existing sanitization techniques, our sanitization using TID is eco-friendly, reusable, which means the chip will be still functional, and also it is more applicable in space. Thank you.